Hi guys, welcome to another video with Miss Hattie. Just want to make sure that I can see my board. So there we go. Okay, so today I'm going to do a little video on functions. And the most important thing about functions is to know that their definition is for every input there exists only one output. So there's the definition. So remember, a function is a function if for every input there's exactly one output. One output. Trying out a new dry erase board. Comment to let me know how you feel about that, okay? So we're also going to talk about multiple representations of functions also. So a function can be represented in multiple ways. And we're going to talk about that. So I'm just going to give you a quick one. Easiest, when in doubt, you make a table of values, right? So a table of values is one of them. Once I have a table of values, I can also make a graph. Okay. I can also make a sequence. We'll talk about all of these. I can make formulas or equations. There's two types of equations we can make for functions. It's the explicit equation. And what the explicit equation tells us is it gives us any direct input and output relationship at any given time or input. And then we also have the recursive equation, which is the one that builds itself from a previous input and output. And the recursive equation is closely tied to the sequence because it's kind of like the instruction manual on how to build a sequence. So I have a table, a graph, a sequence, an explicit rule, a recursive rule, also known as explicit equation and recursive equation. And I also have a contextual representation. So context, like a story. Okay, and so I'm going to give you an overview of this, exactly this right now. So we're going to start off with linear functions first, and then I'm going to move on to exponential functions, and we're going to go ahead and represent them in this manner. So linear functions, as I'm erasing this, we're going to go ahead and give an overview of linear functions. What do we know about linear functions? Linear functions have this very important characteristics that their growth rate, bloop, bloop, bloop. Can you see that? Okay, let's see. My growth rate, I hope you can see that, is a constant additive, or a number that doesn't change and adds to get to the next input and output. So constant additive. Constant additive, I'll call that a CA for constant additive, okay? So I'm going to give you a quick little story. And we're going to go ahead and represent the linear function. Actually, I'm going to go ahead and do the explicit rule, recursive rule model. Okay, so explicit rule and recursive rule formula for linear functions. Okay, so if we know a linear function, that also means y equals mx plus b. So explicit rule looks just like that. Our explicit rule in terms of function notation is going to be like this. And it's going to give me my slope, which is my constant additive. So I'm going to put it right here. My constant additive is going to be my slope, okay, times x plus f of 0, okay? So I also have another formula that I use, and it's one where I don't really need to use f of 0 for the input. I am able to also use this one. Let's see if we can see my board. Okay, m. Actually, let me do it in a different color because that green is a little funky. So f of x, it's going to be my slope. And I use an input and output correspondence relationship here. So that's my input and that's my output, okay? And now for the recursive rule. The recursive rule, again, I said it builds from the previous input and output. So that's an output, and I'm going to build from the previous one. So, and then I'll have my constant additive. And normally I always start with f of 1 equals something. So this right here gives me the roadmap to how to create a sequence. So this says, to get to the next output, I look at the previous output and I add the constant additive to it. Given that I have f of 1, which is the input, of 1 gives me this corresponding output, whatever this is. So I'm going to show you what that means looking at a random situation. So I'm going to talk about, let's see, here's my context. And I'm going to go ahead and build a table of values, see this explicit rule, recursive rule, and then we'll go ahead and graph it as well and create a sequence so you can see the multiple representations of linear functions. So let's say you have $10 saved up already. I'm going to put $10 saved up. Every Sunday, your abuelita gives you $4 more, right? That's just my context. So let's see. We're going to go ahead and annotate. I have 10 bucks already saved up. What do you think this is? This is something that's already saved up. So I'm going to call this my initial value. Like, before I started collecting money that my abuelita gave me, I already had 10 bucks, right? Every Sunday, that's important, your abuelita gives you $4. So this right here is going to be my constant additive because every Sunday my abuelita gives me $4. Okay, I'm going to have to erase this real quick, but I'm going to make a table of values, and then we're going to come back to that. Actually, I might not have to. I'll just... Okay. So I'm going to push this up. There we go. And here I have another one. Awesome. So let's go ahead and look at table of values here. Oops, sorry. I'm going to make a table of values. Now, when I make my table of values, my input will always be on the left and my outputs will always be on the right. So the variable that represents inputs is x. The variable that represents outputs is f of x, which means the function of x. So this is the output that I get when I apply this input into whatever formula I'm looking at. Okay, so I also would like to know, what am I looking at? What are the two things that I'm comparing here? So when I think about this, I say, I know that I'm looking at money, so money is one of them, but every Sunday is also important, which means every Sunday means time, but specifically it means weeks. So I know that this is weeks and this here is money. So I know you can't see that really well, but we'll go ahead and erase that later. So my inputs represent weeks and my outputs represent money. So this means initial value. I already had $10 saved up before my grandma started giving me $4. So I can represent that quantitatively by saying, before grandma gave me anything, which is time equals 0 or week 0, I had 10 bucks. After 1 week, grandma gave me my $4. So now I have 14 bucks. Let's say that this scenario, I never spent any money. So after 2 weeks, how much money am I going to have? Well, if I already had 14 bucks and then next Sunday comes along and she gives me another $4, that's $18. At 3 weeks, I should have 22. So let's see if we notice something. I notice now that this guy, when I jumped to 10 to 14, I added 4. When I jumped to 14 to 18, I added 4 again. And 18 to 22, I added 4 again. This means that this right here also added by 1, and this one added by 1, and this one added by 1. So I notice that My outputs are changing by a constant additive as well as my inputs. That's important because when I'm trying to look at the inputs and outputs, that's going to be part of my constant additive definition. So we recognize that I have a constant additive of 4. So I'm going to go ahead and bring that up. I have a constant additive of 4. Okay. So f of x started with 10, then 14, then 18, then 22. And I recognize that, oops, sorry. Here we go. I recognize that this was my weeks and this was money. Okay. I do recognize that I do have a constant additive of 4 over 1. So my constant additive is the change, that little triangle means the change in my outputs divided by the change in my inputs. Just like that. So what does this say? This is delta y over delta x. That's a little calculus term, but it's good exposure, you know? So, and I can prove it to you. These guys here can turn into coordinate points, and we're going to talk about that in a little bit. So right now, from this situation, you saw the context, which was the grandma situation, and you also now see that I created a table of values. I'm going to go ahead and also graph this to see what I'm looking at. So my f of x is always going to be that axis there. So notice that I have 2, 4, 6, 8, 10, 12, and I'm going to go probably by 4s or maybe 8s. 8, 16, 24, 32, 40. Okay. So notice again, I'm going to go ahead and label this. This is my money and this is my weeks. So what I'm going to do is I'm going to take this point. This is an input and output correspondence. Input 0 corresponds to output 10, which means that at 0 weeks, I had $10. Input 1 corresponds to output 14, which means at 1 week, I had $14. Input 2 corresponds to output 18, which means at 2 weeks, I had $18. So I'm going to go ahead and label that on my cell. 0, 10 means no output value, but no input value, but an output value of 10. 114, right there. 218, see, right there. 218 and 322. So if you notice, my points are a nice little straight path because this is a linear function. And again, it's because of this constant additive. So now I'm going to go ahead and build the recursive rule. I know that my constant additive is 4. It's actually 4 over 1 because I rise 4, run 1, rise 4, run 1. So I'm just going to simplify that to a 4. I know that. I'm going to use any input and output. So I'm going to use the input 2 and the output 18. So this is going to turn to this f of x point, which is 2, 18, and it's right there, that point right there, 2, 18. Okay? But watch what I'm going to do. I'm going to plug in my explicit rule, and then I'm going to also do my recursive rule. So I'm going to start with my explicit rule. My explicit rule says I have a slope, which is my constant additive, and then I have x minus in plus out. Remember that the only thing I have to mess with is my constant additive. That's my constant additive, my input and my output. So I already know that my constant additive is 4, my input is 2, my output is 18. So all I'm going to do is plug that in, and then I can leave it in that form. This is technically point slope, or I can simplify it into a mx plus b format. So watch. Notice that everything that I didn't touch stays as is. So this x and this f of x never get manipulated. My constant additive is 4. I have x minus 2. My formula says minus here, so don't trip out on this fact that this is a positive 2 and over here it's a negative 2. That's because my formula subtracts it. So that's there. And then plus 18. Okay? So I can leave it like this. This is my explicit rule here, or my explicit equation. But I can also simplify it if I do some distribution here. This gives me 4x minus 8 plus 10, which gives me 4x, plus 18, my bad, plus 10. So this right here is the simplified version. F of x equals 4x plus 10, which gives me my slope, my constant additive, and also my f of 0. If I go back to my table, f of 0 is 10, and it's right there. So that's my explicit rule. Okay. So now I'm going to go ahead and build, and I'm going to build my sequence right here. What is the definition of a sequence? The sequence is a ordered list of the function's outputs. So here are my outputs. And normally our sequence wants to begin with f of 1. So that means I don't start with 10, I start with 14. So I'm going to do my sequence here. And my sequence is the following: 14, 18, 22, dot, dot, dot. So now watch, I'm going to go ahead and build my explicit rule. I'm going to remove all this craziness here because I don't want to confuse you. If you want to see that again, just rewind my video. So I have 14, 18, 22. Here comes my recursive rule. Remember that the recursive rule says to get the next output, you look at the output previous, at the growth pattern, which is a constant additive this time, given that f of 1 equals something. That's the rule. So I'm going to go ahead and apply it. Remember, my constant additive is 4, and nothing else changes, just this guy and this guy. So watch. Here's my rule. F of x equals f of x minus 1 plus 4, because that's what I'm starting, my constant additive, given that f of 1 equals 10. I mean, equals 14. My bad. Okay. So let's see if that makes this makes sense. To get the next output, I look at the previous one, add 4 to it, and the first output I'm going to be looking at is 14. So let's see if that makes sense on the sequence. 14, I want to get to the next one, so I have to add 4 to it, so 18. Because I didn't want to get to the next one, I add 4 to it, that's 22, and so forth. Cool? So now looking at this situation here, that's an overview of linear functions. So I gave you a graph, a table of values, a contextual representation, a sequence, a recursive formula, and also an explicit formula. So I'm going to go ahead and now look at exponential functions. Move my camera. Sorry, guys. We're still novices here. Okay. So now we're looking at exponential functions. So remember that the growth factor or the growth pattern for linears was a constant additive, while for exponential functions, our growth pattern is a constant multiplier. Constant multiplier. Cool. So again, we're going to go ahead and start with a little context. So, bloop, 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 bloop. And this context is very relatable right now because, you know, coronavirus, como dijo la Cardi. So, I was going to say, we're going to talk about, we're going to call this the happy gene, okay? Okay. You tag people with the happy gene. You tag people with the happy gene. I'm just trying to stay positive during these times, guys. Okay. Okay. Here is your table of values. Okay. So you've tagged people with the happy gene, and this is the table of values that you have. I'm gonna call G of X so that way we say, okay. So this happy gene started with yourself. There was nothing before, so this is gonna be time. And this is number of happy genes. Happy genes, okay? So what do you think how do you think this table is behaving? Do you think it's adding by a certain amount? So if it's adding by 1, then this should have been 3. So it's not adding by a constant number. It's actually multiplying. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and so forth. So I recognize that I have a constant multiplier of 2. Okay? So your happy gene is actually doubling. So I'm going to put here happy gene doubles. Cool. So now I'm going to go ahead and now that we know the definition of a sequence, I'm going to go ahead and put the sequence here. And the sequence is just an ordered list of a function's output starting with f of 1 or g of 1 at this case. So my sequence is going to be 2, 4, 8, 16, dot, dot, dot. And those dot, dot, dots means it continues. Okay, so let's build the explicit rule this time. I mean, the recursive rule since I have the sequence. And if you'll notice, the explicit rule, the recursive rule is going to be very similar to the linear function, just that instead of a CA, it's going to have a CM. But the rest of it is correct. So the recursive rule will say, and I'm using g of x because this is now a new function. So you can use h of x, g of x, p of x, as long as I'm bringing 2 functions into this lecture. So that's why I'm changing the letters. G of x is equal to g of x minus 1. To get to this output, I look at the previous, but this time, instead of adding, I multiply by that constant multiplier. Given that, I know what the output is for the input 1. So go ahead and build that function recursive rule. So I have g of x is equal to g of x minus 1. Remember, nothing changes, just this homie and that. I got to multiply it by 2 because I got a multiplier of 2, given that g of 1 is 2 because that's the first output I'm looking for. And it's always the output that corresponds to 1. So let's see if that matches. This tells me the instruction manual to create the sequence. Let's see. You start at 2 because that's the output that corresponds to input 1. So there it is. And to get to the next output, you always multiply by 2. Okay, 2 times 2 is 4. Awesome. 4 times 2 is 8, right there. 8 times 2 is 16, and so forth. So this right here is my recursive rule. So far, so good. I hope so. So now, that's my recursive rule in my sequence. I'm going to go ahead and now build my explicit rule. And so my explicit rule or my explicit equation, ER stands for explicit rule, is going to always say f of x, and it's all, I will give you 2 versions. I will always give you the version that has f of 0 on it, or the version that has the input and output correspondence. So here comes the f of 0 one. This one says, as long as I know f of 0, I can add it like this, okay? But this can also be written in this format. F of x is equal to an output times a constant multiplier to the power of x minus whatever input these two correspond to. So I'm going to show how to take an input-output correspondence and then using my exponent rules. If you haven't seen that video, go back and see Ms. Hadigi's awesome exponent rules. And I'm going to be able to simplify this to this. So like with linear functions, I was able to simplify from the input-output point-slope situation, simplified it through distribution, and it got me into mx plus b format, which is the f of 0 format. But here, I'm able to use that exponent rule. So here we go. I'm going to first showcase this one, and I'm going to use 3 and 8. That's going to be my input. So my input is 3, my output is 8. I know my constant multiplier is 2. Okay? So here we go. F of x is equal to, what's my output? 8. Times my constant multiplier, 2, to the x minus 3 power, right there. Why? Because 3 is the input, 8 is the output, and 2 is the constant multiplier. My format tells me right there what to do. Okay, so this right here is a very valid explicit rule, but sometimes some people would like to simplify it, and we can, and I'm going to do that now. I'm going to first take this 2x minus 3, okay? So I'm going to just go like that. So you can see that that is my explicit rule. But I'm going to go ahead and take my 2x minus 3. And I'm going to notice that I have subtraction in my powers, which means I'm able to use my diff tract rule. Again, if you haven't seen that video, pause here, go back to see my exponent rules video, and then come back and resume this. So this really means that I have 2 to the x over 2 to the third on the bottom. I recognize that 2 to the third is 2 times 2 times 2, which is 8. So this really means 2 to the x over 8. So this 2 to the x minus 3 simplifies to 2 to the x over 8. So watch what I'm going to do. I'm going to go ahead and now plug that in to this one here. Instead of writing 2 to the x minus 3, I'm going to write it like this. So I have f of x equals 8 times 2 to the x over 8. Now here, the 8's cancel. And what am I left with? I'm left with f of x equals 1 times 2 to the x. And let's see if that makes sense. Remember I said that f of 0 and no power here, no subtraction of any value against the power? Well, that's really because x minus 0 is just x. It's still this format, but it's to the 0 particular. So let's see if it's true. 1, is 1 the output that corresponds to 0? It is. It's right there. So this is the simplified version. That is the explicit rule right there. Okay? Good thing about this is that you can go back, repeat, review, rewind, and let me know if you have any questions. You can always set up a chat right here, or you can email me on my website. All of it is linked here on my YouTube channel. So I'm not done because here I go. I'm going to go ahead and now create the graph. So we're looking at the graph now. So far for the exponential function, we got a scenario. We got the explicit rule, the recursive rule, the sequence, the table of values, and here comes the graph. So again, we're recognizing that we're looking at this. There we go. This formula or this explicit rule, and we're going to go ahead and graph it. Okay, so I'm going to go by halves on my inputs. So what does that mean? Every 2 lines is 1, which implies that every little line is half. That's what I mean. And here I will go by ones. Okay. So given this context, it is a discrete function because my grandma isn't giving me money at every single point in time. She gives it to me. Oh, sorry, wrong scenario. The happy gene is only being doubled at a one specific time frame. So I'm going to go ahead and graph it. So at 0 corresponds to 1. Here's my table of values. Eek. This is where I miss my students because they will always correct me and be precise in my stuff. But it's g of x. So on the other one, it should be g of x too. Mis perdones right there. So I have 0 corresponds to 1, 1 corresponds to 2, 2 corresponds to 4, 3 corresponds to 8, 4 corresponds to 16. If you notice, my explicit rule does tell me exactly what I want. So let's say I want g of 5. Let's just put an example. I want g of 5. What is g of 5? I don't know, but if I plug it into my explicit rule, it'll tell me. So I know my explicit rule says g of x is 1 times 2 to the x power. So if I want to find g of 5, wherever there was an x, I'm just substituting the value. So I have 1 times 2 to the 5th. And 2 to the 5th is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. So that's, if I was to continue this, that gives me 32. But I can also figure it out through the explicit rule. Okay? Okay, so now let's go ahead and graph it. 0 corresponds to 1. 1 corresponds to 2. Always, always, always label your graph so you know what you're doing. 2 corresponds to 4. Now notice there's already kind of a little curve right there. 3 corresponds to 8. 4 corresponds to 16. So if you notice, this already has a curve here. So I'm going to just showcase the curve. Bloop, 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 bloop. Right? Do you see the curve? And this is why people need to understand the power of exponential functions. Here, at the beginning, the growth doesn't really seem relevant or doesn't really seem extravagant. But once I get here, notice that it went from this little tangent to this little tangent to this. Now imagine over here on the top. So that's where exponential functions are very powerful because that multiplier takes you from very simple growth to larger values. So 6 corresponds to 64, 7 corresponds to 128, 8 corresponds to 256, 9 corresponds to 512, and so forth. So that's why they're important. So here you go. These are an overview of linear and exponential functions. A quick overview to summarize this video. If you have a linear function, okay, and then I'm going to also compare exponentials. Okay, so if you have a linear function, you have a constant additive. If you have an exponential function, you have a constant multiplier. Okay, so that's what we know. The graph is a line for a linear. Over here, the graph is a curve for the exponential. Okay. My explicit rules or my recursive rule, let's start with the recursive, that one's easier. Again, f of x equals f of x minus 1 plus my constant additive such that given that f of 1 equals whatever value, the recursive rule for an exponential, f of x equals f of x minus 1 times a constant multiplier given one particular output that corresponds to 1. Okay. And here comes the explicit rule. Again, I'll start with the input-output one, and then I'll end with the simplified version one, which is the, oh my bad, that was bugging me, the f of 0 format. So the first one again is f of x equals constant additive x minus in plus out, which when simplified looks like this: f of x equals constant additive of x plus f of 0. This is just y equals mx plus b right here. F of 0 is the y-intercept, which is f of 0 by definition of functions. Okay, good. Okay, here comes the explicit rule for an exponential. F of x equals output times constant multiplier to the x minus in, okay? And when simplified, and you have to diff track to simplify, f of x equals f of 0 times constant multiplier to the x, okay? Hope you enjoyed this message or this video. I will be posting domain and range next. See you guys.